first of all, we need to discuss the selection rules. That when this can happen, that when the electron changes its state with some quantum numbers to another state with some quantum numbers, how radiative transition happens and for which state radiative transition can happen. Now we don't have any kind of limitation on the principal quantum number or the total quantum number, because electron can go from one quantum state to another quantum state, like it can have like initial value ni, if we know the initial value ni, and if we know the final value, initial value to final value, we already know that h mu is equal to ef minus ei, right, which depends on principal quantum number, and we know the relation of this, and the frequency of that radiated line is mu, and the energy is h mu, right? So now the most important thing is here is that now this is the energy lines are not only splitted or have not the confirmation for only principal quantum number. The energy levels got splitted with respect to ml, the magnetic quantum number as well. So we have to see that from which ml, like if we have n is equal to 2 and L is equal to 1, so for L is equal to 1 we have three values of ml, and this is something like 1, 0, minus 1, and for n is equal to like 1, this is L is equal to 0 state, and there is this ml is equal to 0 only. So from where to where this transition can happen, like if electron is with these quantum states, n is equal to 2, the psi and lm is ml is equal to psi 2 1, and ml is 1 as well. So is this transition possible, that electron can go from here to here? Is this transition possible? So we have to apply some selection rules, and we need to discuss this by applying some quantum concrete results, right? And what are those quantum results? Now these transitions are limited by selection rules, and from where we get these selection rules? Now this is the important thing. Particularly, we know that from n is equal to n state, if we apply the quantum numbers, principal quantum number, we already know the transition happens, and from different to different principal quantum number or different quantum state. And we discuss this thing, that from within a one stationary state, electron does not radiate. But when these stationary state changes, or when electron goes from one orbit to another orbit, it radiates. And this integral must not be equal to 0 when electron is going from one quantum state n to another quantum state m. Now this integral need not to be 0 for a transition or for a radiative transition, right? So this need not to be 0. This must not be equal to 0 for the transition. And we already found out that why this must not be equal to 0. Because from here we concluded that h mu is a result of E final minus E initial. We found out this using this integration. We already discussed radiative transition in the earlier classes, right? So this integral cannot be 0 for the allowed transitions, and if this integral is 0, then that transition is forbidden. So this also depends on principal these quantum numbers. And now the wave function is something like this: psi n l ml, and for allowed transition this must not be equal to 0. So when we put u x y z something like this, then the allowed transition condition comes out to be with some limitations, and those limitations are, when we solve this, we already know that for a particular quantum state like psi n lm is equal to psi 211, and next psi n dash l dash ml dash n dash l dash ml dash, this is equal to a different state, this one is different state, and when we solve the integration, if this is not equal to 0, then that integration is a allowed one, or that transition is allowed one, otherwise that transition is not allowed, right? So from this integration we got that actually del L, whenever del L is equal to, now n is not limited, the principal quantum number is not limited, right? But del L, the transition is limited by the change in orbital quantum number, which is limited by that L can have a plus value, plus 1 value, or a minus 1 value. Initially, if L is equal to 2, then electron can go from L is equal to 2 to next L is equal to 1 or L is equal to 3, but electron cannot go to L from L is equal to 2 to L is equal to 0. This cannot happen. So this is a selection rule. And similarly, ML, del ML can be 0 or only plus minus 1. This cannot be equal to plus minus 2, plus minus 3, something like this. And we will see this, okay? The ZEEMAN effect splitting, we will see this. So N is not restricted, but L can only change by plus 1 or minus 1, and ML does not need to change. Maybe ML does not change, then del ML is equal to 0, or if it changes, then this is plus 1 or minus 1, then del ML is equal to plus minus 1. So now we already know that ML can have 2L plus 1 values from minus L to L, or a state of a given L is splitted into 2L plus 1 value substates, then differ in energy by mu B. We already discussed it. This is equal to mu B. We got this result from here, right? We actually found out this result. That now this is mu B, and ML can be plus minus 1, then the magnetic interaction energy can be mu B into B, right? So the substates differ in energy can be mu B. This depends on magnetic field whenever the atom is placed in external magnetic field. Otherwise, these states merge into a single state, right? There is no need of the differentiation of these states or splitting of these states into different states, sublevels. These sublevels happens when we place the atom in external magnetic field, and we got this, that why this happen, right? We already found out it. So when the atom is placed in external magnetic field, now we are going to discuss the transition. Now let's look into this. First of all, initially the spectrum without magnetic field. Now this is the spectrum without magnetic field. Now now I am not applying here any magnetic field. This is the characteristic frequency of a transition when electron goes from L is equal to 2 to L is equal to 1. Now you can assume, or you can see this, that N can be anything here. N can be anything. N can be 3 here, N can be 4 here, N can be 5 here, or anything. And N can be anything here as well, right? If N is equal to 2 here, N can be 3 here, 4 here, and anything. So for N is equal to 4 to N is equal to 3, if this is the transition happening, then for N is equal to 4, I am taking a particular state L is equal to 2. And for N is equal to 3, here I am taking L is equal to 1 state. Because del L is also limited by plus minus 1 according to selection rules, according to these radiative transitions. This is also limited by this, right? So for L is equal to 2, for any principal quantum number, I am not bothering about the N number. Now for L is equal to 2, L is equal to 1, there is a transition happening, H mu naught, okay? And mu naught is the characteristic frequency of that transition, that radiative transition. Now L is equal to 2 is further getting splitted into 5 different levels. Now why 5 different levels? Because ML can take 2L plus 1 values from minus L to L. Now ML, the magnetic quantum number, for this L is equal to 2 can have 5 values from minus L, ML is equal to minus 2 to ML is equal to 2, right? Similarly, for L is equal to 1, ML can take 3 values. This is already we discussed in space quantization. So the ML is equal to 1, 0 and minus 1. Now how these transitions happens? Now del ML is already limited by 0 and plus minus 1. For when del ML is 0, del ML is 0, from ML is equal to 1 to ML is equal to 1, ML is equal to 0 to 0, ML is equal to minus 1 to minus 1. Now this is a state. Now these transitions are happening. These 3 transition can happen from here to here. 3 transition can happen. All have the same characteristic frequency, right? Similarly, 3 transition can happen. 3 transition can happen for a del ML plus 1. Initially ML is equal to 0, then finally ML is equal to 1, ML is equal to minus 1, ML is equal to 0, ML is equal to minus 2, ML is equal to 1. Now for these transition, del ML is equal to 1. Magnetic quantum number got changed by 1 value. For this state, for these transitions, ML initially was 2, now ML is equal to 1. There is a decrement of ML. ML is equal to 1, here ML is equal to 0, ML is equal to 0, ML is equal to minus 1. Now this is also limited by del ML minus 1. So del ML, according to selection rule, cannot overpassed by plus minus 1. Okay. So what is the frequency of the interaction? Initially, frequency of the transition. Initially, for this state, when we did not apply any magnetic field, spectrum without external magnetic field, this was the frequency mu naught. Now, for these transitions, something different happened, and this is extra energy which got subtracted, right? Which got subtracted from extra frequency. Now this is also the Larmor precision frequency. We got subtracted from this mu naught for this transition level. For this transition, for this mu naught remains same because there is del ML is 0, and the interaction energy, the magnetic interaction energy for ML is equal to 0 will be 0, right? And otherwise this will be the frequency. If I put the energy, then this is equal to h mu, and h mu dash or h mu f is equal to Larmor frequency. Okay, and if I place plug into this value into this, here I will get that mu naught minus eb by 4 pi m, right? And this is for del ML is equal to minus 1. The frequency got added into this characteristic frequency. So these three splitting, I will get. Initially I was getting a single transition. Now I have 3 different transitions, and this is the energy splitting. Now this is the energy splitting, but when I look at the spectrum, the energy spectrum, initially there was only one characteristic spectrum with mu naught frequency, but now I have 3 different energy spectrum with different frequencies. Okay, now these spectrums comes out from these transition. We can experimentally see these spectrum only when electron gets transformed from one state to another state. Okay, so this is only applicable when this happens, right? So next further, frequency of these depends on the strength of magnetic field. So mu, and for the first spectral line, this is the frequency of the first spectral line, this much. Second spectral line is equal to the same frequency, characteristic frequency, for which del ML was 0, and this is third state for which frequency got increased because of this magnetic interaction, and the change in frequency is either 0 for second state or plus minus eb by 4 pi m. Okay, now this is important thing. This result is quite important because you can get numerical questions from this question from this result. Okay, so we already know the relation between wavelength and frequency. Mu is equal to c by lambda. So for looking for the change in this, I will apply the differentiation, and this is equal to this much. Okay, in terms of wavelength, Now this will be the result I will get. So here is a question as well. A sample of certain element, any kind of element it can have, means any atom which may be placed in external magnetic field. The strength of magnetic field is this much, 0.3 Tesla. This is less than 1 Tesla. Okay, so this magnetic field, now this strength is very weak and suitably excited. How far apart are the ZEEMAN components of the 450 nanometer spectral line of this element? So what is del lambda? You need to find out only del lambda. Put the value of lambda into this, magnetic field value into this, and electron mass into this, and you will get C, and you will get such a charge. Put all these values and you will get the del lambda. Okay, so this is all, but in a little abbreviation I am going to discuss the anomalous ZEEMAN effect. Now this effect was only in this ZEEMAN effect was only in the consideration that we are only considering the effect of the interaction of L with respect to the external magnetic field. We were only discussing the spectral line splitting with respect to the orbital quantum number, right? Orbital quantum number and magnetic quantum number, magnetic orbital quantum number. But what if there is a spin factor as well? If there is a spin factor, then there is a total angular momentum quantum number as well. And total angular momentum quantum number, or the total angular momentum J takes L is equal to S plus J is equal to L plus S. This is limited by J quantum number, this is limited by L quantum number, this is limited by S quantum number, right? So for these cases, now I need to choose. Now my quantum number is J here, and J is the quantum number which limits this total angular momentum, and there will be for magnetic interaction there will be mj can have 2j plus 1 values, okay, from minus j to j, right? So for this case the space quantization will happen something like this, because the magnetic moment will react with mu j will react with the external magnetic field with and due to this interaction the total angular momentum J will start to precess around the magnetic field, external magnetic field, and then there will be a space quantization, right? And because of the space quantization we can have ZEEMAN effect for that as well. But that ZEEMAN effect is known as, for the spin factor, that ZEEMAN effect is known as anomalous ZEEMAN effect. However, that thing is not in your course. The anomalous ZEEMAN effect is in not your course, but you can study that as well. Okay, so this is the most important topic of the atomic physics, ZEEMAN effect, and this is the most important question which is bound to come every year in your paper. So try to focus on this. If you get stuck anywhere in this topic, ask me, and hope you all are right. Thanks.